We're going to talk about the hypergeometric distribution. This is one that's very similar to the binomial distribution in that we are going to perform experiments, and at least in the simplest form of this distribution, there's going to be two possible outcomes, what we call a success or a failure. I will mention that it's a little beyond the scope of this book, but there is an extension of this distribution to have more than two possible outcomes and still have a hypergeometric distribution. And incidentally, there's a version of the binomial distribution that has more than two possible outcomes. But for now, let's stick with two possible outcomes. And in this case, we are going to be sampling without replacement from a finite population of n items. So imagine you've got a bowl full of marbles. Some are black, some are white, and you're going to reach into the bowl and you're going to pull these out. You can do it one at a time or a handful at a time, but the point is that you're not going to put them back between samples. So you're going to pull a marble out and keep it out, pull another marble out, keep it out, and that's effectively the same thing as reaching in and pulling out a handful at one time and not putting them back. So that's what we mean by sampling without replacement. And the shape of the hypergeometric distribution is similar to the binomial. If the population proportion is 50%, you're going to have a symmetric random variable, otherwise it's going to be skewed in a similar fashion to the binomial. Here are the characteristics. We have three parameters. Capital N is the number of samples in the population, or number of items in the population. Lowercase n is the sample size. S is the number of successes in the population. And then X is the random variable we're interested in. That's the number of successes in the sample. And so basically all we're doing here is we're counting the number of ways that we can choose X samples, X successes from S successes. So S choose X, and then in addition to that we have to count the number of ways that we can choose from the failures, the capital N minus S failures in the population, lowercase n minus x failures in the sample. And all of that's going to be divided by capital N choose lowercase n, or the number of ways that we can choose lowercase n items from capital N items. In Excel, we can use the function hypergeom.dist and put in x and s, capital N, and then the 0 tells us whether it's cumulative or not. So we can actually use this for the CDF as well. The values of x that are possible to go in here are either the maximum of 0 and lowercase n minus capital N plus s. That's on the low end. On the high end, x has to be less than either the number of successes in the population or the sample size, whichever of those is smaller. So there's a similar argument for why the lower end is 0 or this other number. So the mean is going to be n times pi, where pi is the initial ratio of successes in the population, so s over cap n, and the standard deviation is n times pi times 1 minus pi. Now these things look kind of like what we had with the binomial distribution, and sure enough they are. The only difference being with the standard deviation has what we call a correction for finite sample, or sampling a finite sample correction, which says if our sample size is large relative to the population size, we need to take that into account. And if the opposite is true, if the sample size is very small compared to the population size, this is going to effectively be equal to 1. And so let's look at an example. We've got a shipment of 10 iPods, and we know that 2 are damaged and 8 are good. And the receiving department at Best Buy says, well, we're going to test the shipment, and we're going to do that by taking a sample of size 3, and we'll see how many of those are defective. So we're going to say X is the number of damaged or defective iPods in the sample, and So the parameters we have are capital N is 10, that's the number of iPods. Lowercase n is 3, that's the sample size. Lowercase s is 2, that's the number of damaged iPods in the shipment. And so cap n minus s is 8, that's the number of non-damaged iPods in the shipment. And x is the number of damaged iPods in the sample. So this is the number of successes in the sample, which means n minus x is the number of non-damaged iPods in the sample. So you might say the setup we have here is very similar to the binomial, but why is this not a binomial? It's not a binomial because the probability of success changes every time we sample one of the iPods. In fact, we could say, what is the probability of getting a damaged iPod on the first draw from the sample? And that would say, well, how many damaged iPods are there? 2. How many total iPods are there? 10. So that probability is 20%. We'd say, what's the probability of getting a damaged iPod on the second draw? Well, that depends on whether the first one was damaged. If the first one was damaged, then we only have one left that's damaged and 9 to choose from, so 1 over 9th. Otherwise, we have 2 damaged and 9 to choose from. So the probability of having damaged iPod on the second draw is dependent on what happens on the first draw, and that's why this pi does not change, or pi is not constant, and that's why we can't do this like a binomial random variable. On the third draw, we have either 0 if the first 2 were damaged out of 8, or we have 1 out of 8 if one of the first 2 was damaged, or we have 2 out of 8 if none of the first 2 were damaged. And so we need to be able to account for all of that in finding the probability that we're interested in. So here's the entire probability density function for this random variable the way we have it set up. So we have 2 damaged iPods in the population, and so the values of x are either 0, 1, or 2. And so we can write down all these probabilities. What's the probability x is equal to 0? It's 2 choose 0 times 8 choose 3 divided by 10 choose 3. Now notice if I add the 2 plus the 8, I get 10. If I add the 0 plus the 3, I get 3. So that's a quick check you can make. That's always going to be true. So this is just 2 choose 0. Here are all the calculations, and we get 0.4667. If you're using an older version of Excel, you can do this by using Hypergeometric dist 03210. The newer version, you would use Hypergeometric dist 03210, 0. So this last argument is new and is only in the newer version of this function, and that's when you've got to have this decimal point here. So same thing for these other ones. What's the probability x is equal to 1? Well, it's just 2 choose 1 times 8 choose 2 divided by 10 choose 3. Again, notice 2 choose 2 plus 8 is 10. 1 plus 3, 1 plus 2 is 3. So quick check, I've got that right. And it turns out to be the same probability that x is equal to 0. And then I've got probability x is equal to 2. 2 choose 2 times 8 choose 1 divided by 10 choose 3. So again, 2 plus 8 is 10. 2 plus 1 is 3. And plug all that in, and we get the probability of what we are looking for. So there are lots of different examples where the hypergeometric distribution can be used. Most notably, if you're going to find the probability of a certain hand in a poker deck, and a 5-card hand of poker cards, the hypergeometric distribution is going to be the basis for those things. So that's all I've got for this this hypergeometric distribution video. Look for a couple of example problems from last week's homework that I'll put up here. We'll walk through a few of them and show you how to solve them. And if you have questions or want to see any others, please send me an email and let me know. I'd be happy to make a quick video going through some of the other homework questions. So we'll see you in the next video.